Welcome back to Electronics, Simple Circuits and Measurements Fundamentals. In the previous module, we set up our multimeter and explored the use of the continuity function by mapping out our breadboard. Now, let's dive into what's going on inside of that multimeter we love so much by defining the physics of electronics. You've certainly heard of the electron before. It's the negative charge carrier of the atom, one of the fundamental building blocks of everything around us. In this section, I'll draw a comparison between how electrons move and the behavior of water molecules, since the behavior of water is far more relatable. Let's start by defining a few key things. First, moving electrons flow in a current, much like water droplets create a current as they flow together down a river. Second, something called potential energy is what motivates current to flow. This electrical potential is more commonly called voltage. Lastly, certain circuit elements exhibit a trait called resistance, which inhibits the free flow of current, much as boulders and dams restrict the flow of a river. Let's explore this water analogy a little bit further. Here we have a diagram of a magnified copper wire with some electrons floating around in it. The fact that the electrons are simply freely floating around inside of this wire is characteristic of conductors. Conductors allow for the free flow of electrons. If we place a battery within this loop of wire, such that the positive end of the battery and the negative end of the battery are connected by the wire, the battery will motivate the electrons to move from its positive end to its negative end. This is similar to how water will fall from a source such as a water tower. When the water is held high above the ground, gravity pulls it down. As we said before, this motivation of current, provided by the battery, is called voltage or electrical potential. When the electrons flow, this is called current, much in the same way that water flowing downhill is called current. Where voltage is intuitively labeled with the letter V, current is often denoted with the less intuitive letter I. We had also mentioned something to do with the restriction of current, similar to how a boulder will inhibit the flow of water through a stream. An electrical component specifically designed to restrict the flow of electrical current is called a resistor. Resistors convert the flow of electrical energy into heat, and in turn, they reduce voltage. You may think of this like water flowing through a hose. If we constrict the hose, it reduces the water pressure and slows the flow of water through the hose. When dealing with resistors, you may notice that these small components sport a colorful headband. Typically, these colored bands appear in a set of 3 or 4 colors. The colors designate how much the resistor will, resist. The unit that we use to describe how strongly a resistor will resist is called an ohm, represented by the capital Greek letter omega. Take a moment to Google search the term resistor chart to see which resistances each color represents. Before, when we were using our multimeter to explore continuity mode, you may have noticed that the continuity symbol was found near a capital Greek letter omega symbol. This multimeter mode will allow us to measure the resistance of any given resistor, saving us the time and effort of memorizing a resistor chart. Although, one may argue that memorizing the chart will save you more time in the long run than using the multimeter every time you come across a resistor. Regardless, let's take a moment to measure the resistance of the resistors you've selected from your kit. When you measure them, refer to the resistor chart you Googled earlier to compare your measurements to their theoretical values. Do they match? Pause the video and take some time to play. When it comes down to the nitty-gritty details of how the multimeter operates, every multimeter function is based on a voltage measurement. The multimeter is able to relate voltage to quantities such as current and resistance through an incredibly simple and important equation called Ohm's law. Ohm's law states that voltage is equal to the current flowing through a component multiplied by the resistance of that component. Using algebra, if we know or control 2 of these quantities, we can solve for the remaining quantity. There is, however, one small detail that is often overlooked here. Ohm's law specifically calculates a voltage difference across a component. That is to say that the term voltage is not particularly useful without asking what the voltage measurement was made relative to. In short, if there is no resistance between 2 conductive points on a circuit, then there is no change in the voltage between those 2 points. They are at the same electrical potential, or voltage. Using our water analogy, measuring the gravitational potential between 2 points in a body of water that are the same elevation means that, well, you've found yourself a lake. It's only a river if it flows downhill. Let's put this to the test. We mentioned before that the battery was responsible for producing a voltage and motivating current to flow through the wire. Let's change our multimeter dial to this voltage mode and use our probes to measure the voltage between the positive and negative terminals of the battery in your kit. Pause the video and explore this for yourself. What did you find? You may know that this battery is commonly classified as a 9-volt battery. But was your battery's voltage exactly at 9 volts? It so happens that a fully charged 9-volt battery typically sits well above 9 volts, sometimes getting close to 10 volts. However, a battery that has been drained past 8 volts is typically considered dead. Also, you may have seen negative voltages when measuring your battery. Why is this? If you didn't see it, what could cause this? It's probably because you have your probes attached to the battery in the wrong order. Remember, the black probe, typically connected to the COM port of the multimeter, is used as your reference, or zero. Since electricity flows from the battery terminal with positive voltage to the one with negative voltage, swapping your probe order means that your multimeter thinks the positive terminal of your battery is your reference point, and the negative terminal, at the lower voltage, is what you want to measure. But what is that symbol in front of the voltage icon on your multimeter? You may notice that there is another similar icon next to another V along the dial. Well, the voltage mode that we used before is called direct current voltage mode, or DC voltage mode. This is because batteries motivate current at a steady rate in one direction. Although the battery may drain slowly over time, the overall effect is that the voltage it produces is constant across time. This is different than the other voltage mode, the one with a little squiggly tilde symbol next to it. This is called alternating current voltage mode, or AC voltage mode. In some circuit applications, it is necessary for the source voltage to oscillate between two levels. We'll save this for another workshop entirely, but this is what you'll find in something like a common wall outlet. Before we move on to our hands-on circuit activity, let's review 3 key items that we've learned so far. First, ground is ground and power is power. If we connect 2 points on a circuit with a conductive material, then the voltage along any point on that conductive material is the same. This is to say that attaching a wire to the positive terminal of your battery means that the entire wire sits at 9 volts relative to the negative terminal. Next, Short Circuit is more than just a great movie. Go find it and watch it if you haven't seen it. This will not only superheat the wire to a point where it will eventually burn and break, potentially burning you, but it could also cause the battery itself to heat up and boil the acid within. This is, of course, very bad. You can always check for shorts in your circuit, be they intentional or non-intentional, using continuity mode in your multimeter. Finally, voltage is measured as a difference. We learned this from Ohm's law. If 2 points in a circuit are directly connected to one another via a completely conductive material, then there is no voltage difference between them. On this subject, we will often call the reference voltage of a circuit ground, meaning 0 volts. This comes from the fact that the Earth is the ultimate reference for all things electrical. Since it effectively never changes its overall voltage, Earth ground is used as a universal reference for many electrical measurements. We'll see you in the next module where we will share a hands-on activity exploring the behavior of circuit components that we've discussed when they are hooked up together. See you then!